So hi everyone. We are the Deepform team, and this was a project that I've been meaning to do for several years because it comes out of actual frustration and money and time spent. So I'm a computational journalist. I've been teaching at Columbia the double masters in computer science and journalism for a while, and so I basically do two things. I try to apply computer science to journalism problems, and I try to do journalism around the ways that computer science is changing society. And Nick, you want to introduce yourself?
My name's Nicholas Barty. I've done a bit of machine learning in the past, not a lot of deep learning. We started here at Weights and Biases about 8 months ago, so I've been learning and really loving it.
And Nick was super helpful in getting Weights and Biases to work for this project, so I recommend an insider on your team whenever possible. So the problem basically comes down to that public data is kind of nasty. There are laws saying that you have to disclose certain things. The laws don't require that you disclose them in machine-readable formats. So if you go to this website, you can learn who's spending money on campaign finance or political advertising, but not easily. In particular, there's no systematic way. There's no database of this stuff. So this is what the problem looks like. Here is a form that a TV station publishes, and we're interested in a few pieces of information like the total and the call sign of the television station and who the advertisement is for. Here is another form. It's the same information. In this case, the total is on a different page because these are multi-page documents. Here's yet another form, and so on. There are literally hundreds of different types of forms, and we're trying to get the same small set of information from each one. So the goals of this particular project was less about extracting the data, because as you'll see, the training data we use is from 2012, so it's no longer interesting to journalists. More about proving that it's possible, that this is a good idea, because the journalism profession is starting to gear up for the 2020 elections. And the last time somebody decided to do work with this data systematically, they did a massive crowdsourcing project. This was a project known as Free the Files, wherein they convinced thousands of people to transcribe 17,000 of 40-odd thousand files. Now, I don't think this is a reasonable way to go about this. I don't think you could do this again because it's less novel. It's harder to get people to do it. But it did provide some really amazing training data. So after suitable processing, this is what that training data looks like. We knew that the geometry was going to be important, and this wasn't just going to be like just extracting the text wasn't going to work, because you need to be able to match column headers and this sort of thing. So we decided to go with this like tokens with bounding boxes, and you can see there that's the target token, right? That 1170 is the total, and we know from the training data, which are the crowdsourced data, which, by the way, looks like this. This is the result of thousands of hours of volunteers typing in stuff. So from that, we get this type of data. So as a baseline, I spent all of 30 minutes writing the dumbest extractor. We decided to start with the totals because it's easy to identify dollar amounts, and so we figured we'd have an advantage right off the bat. If you just look for the word total, wind up with a number, you get about 60%. I bet I could push that up to like 80% if I really worked at it, but that's a good baseline for sort of how hard this problem is or isn't. So then we got really fancy. So we started thinking, how are we going to encode the input and output? And we thought, okay, well, let's just throw the whole document, right? Let's just say, up to 4,000 tokens or something. And then get an output for every one of them. And that's way too many inputs and outputs for a fully connected network. But we do need long-range dependencies, because a column header here could tell us something about a token down there. So we tried this UNet thing, partially because I used to do computer graphics, and so I really liked image pyramid stuff. But partially because the convolutional structure meant many fewer parameters than a fully connected network. If densely connected, this would be in the billions of parameters. Totally failed, by which I mean wouldn't even train. Yeah, my other logic there was like, yeah, tagging tokens is kind of like segmenting pixels, right? Like maybe, sort of. Anyway, not the case. So we had to go back to the drawing board, and we said, well, okay, let's just make everything much smaller and run on Windows. After all, if I can get 60% accuracy just by scanning tokens sequentially, maybe I can do something with a 20 or 30 token window, because usually the header that defines the value you're looking for is pretty close, and the PDF extraction it runs in raster order, so usually it's kind of nearby. And so that vastly reduces the size of the network, but it introduces a complexity, which is that your prediction isn't just running the model. Now you've got to run the model on every window and combine the windows somehow. So I said, okay, well, we'll just sum them and see what happens. And we went with basically a fully connected network. This is like classic 1950s multi-layer perceptron stuff, right? The only difference is that we've got mild cleverness on the token representation. So we've got like a word embedding layer, and then we augment that with the geometry and some hand-engineered features, which I'll get to in a second. So that vector is for one token, and then we repeat that for the 20 tokens in the window. And then we take that whole thing, flatten it, and run it through a dense network with some dropout. And it totally worked. If by work you mean we can get the loss to 0. What it did is learned to guess all 0. Right? And you can see it actually destroys what accuracy it had. And the basic issue here is that the loss function on the network is a loss function on the window, and we don't care about the loss function on the window. We care about the loss function on the document. And so decoupling these things makes the training fall apart. So eventually what I put together was a custom loss function. This is my terrible TensorFlow code. I'm sure there's like a one-liner for this. All I want to do is I want to penalize false negatives more than false positives. Right? So that's all I'm doing. And that worked. It started actually learning, and we got to sort of 80 or 90% accuracy almost right out of the gate. You'll notice that the document accuracy, and so here you can see the training and validation. First of all, the training and validations are almost identical. And second, they're way noisier than the accuracy on the actual window output. And that's because, again, the thing we care about is not the metric we're optimizing for. I've just tried to couple them as closely as I can through the loss function. And then we started to get fancy. This is where Nicholas started to show me the utility of the weights and bias product. And we tried playing around with there's a lot of parameters. There's like at least a dozen sort of knobs you can turn on this. And we discovered that, it was a broadly effective network, but some parameters did way better than others. In particular, there's this one parameter here, which is the penalty for false negatives in the loss function. So all of the really good outputs where you start getting like 90% are all around 5. So what that's saying is you have to penalize missing the identification of the correct token about 5 times more than guessing a token when guessing the wrong token. This is particularly interesting, by the way, because the many windows are empty. So if you take like a 20 token window of the document, most of them won't have the value you're looking for. So you have to be able to guess that there's nothing there as well. So we also had to do some work balancing the classes, and this is a hyperparameter on sort of what the class balance is. Turned out not to have a huge effect. Okay, so part of this was these hand-engineered features. And I stole some code from my hand-coded baseline, and it's just a little regex that says, is this a dollar amount? And, it's $sign and some commas and a .00 or something. And like it kind of feels like cheating, right? Like, why am I throwing machine learning at this when I'm sitting here hand coding everything? So we started experimenting with this a little bit, and we found that we get about a 10% improvement by throwing these types of features in, which is pretty substantial. And then I actually went down to the Stanford AI lab on Monday to talk to a team which has also been playing with some AI for journalism stuff, and they pointed me to this paper. So I finally discovered the research literature on my problem. This is known as knowledge-based construction, so here you can see this like transistor data sheet, and to extract the fact that the collector current for this particular transistor is 200, you need to know all of these relations between like stuff up here and stuff up here and alignment and fonts, and you need to use the text. So this design is actually sort of conceptually similar to what we ended up doing with these augmented features. And here's the fun part. It works on weak labeling functions, very much like the hand-engineered is this a dollar amount function. So you saw the Snorkel presentation a few weeks ago. So it actually uses Snorkel to generate training data, but there's no reason you can't use weak labeling functions to generate features. And this is actually how one of my favorite AI systems works. It's anyone remember DeepQA, the Jeopardy winning machine? So that was pre-deep learning, and what that actually uses is hundreds of different types of question and answering modules, each of which is hand-engineered to guess at a particular type of question, and then the machine learning just figures out which answer to use at which time. Anyway, it turns out that this problem is hard. I now know why nobody had done this before, and the general problem is actually quite tricky, and you have to combine a lot of different types of engineering, and we still have to do feature engineering to make this work. Okay, so in short, we've gotten far enough to demonstrate to the investigative journalism community that it's worth investing their limited resources in trying to build systems like this or trying to process their data in this way. Figured out what the problem is called in the research literature, figured out that it's hard, and also we produced a training data set, which hopefully others can take up to advance the state of the art in journalistically relevant data extraction. Thank you.